Hello, today I'm going to be going over an electrostatics problem, one on Coulomb's law, and this is actually from the Griffiths textbook, and let's take a look and see what we're dealing with here. So the problem is asking us to find the electric field at a distance z above the midpoint between equal and opposite charges at a distance d apart. So the first thing we should do is create a drawing of our problem to help us understand how to approach it. So I'm going to create a plane here. So right here I have my z-axis, and then right beneath I'll put my x-axis. The reason I'm doing these is, remember, we have a distance z above the midpoint. So we have some point here, and we also want to look at these equal and opposite, between equal and opposite charges. Yeah, between basically a q and minus q. Let's see. Yeah, equal and opposite charges is referring to just a positive and negative q charge. And we see that they're a distance d apart from each other. And I'm just putting them on the x-axis because that's the easiest thing to do. But I can have, let's say, q here. And I'll have my negative q here. And we're going to say that they're a distance d apart. So from the z-axis, they're both d over 2 from it. So let's kind of draw our electric field contributions from each of these points, or each of these charges, to our point on the z-axis. So I'm going to draw my first electric field here. And we'll call that E1. And then I'll draw my second one. And you can actually see, since it's a negative Q charge, the electric field will point towards it, and it's from the other side. So we can simply just say that this is our other electric field. So try to see if that makes sense. This is negative Q. And once you see that, you should see that our resultant electric field will simply be this right here, right in between both, which is basically the total electric field from both of these charges. So what you should notice is that the y components, or sorry, I should say the z components, in the z direction, our electric field components cancel out. So I'm going to say we cancel in the z direction, but we add in the x direction. Okay, so using superposition, we can say that our electric field is equal to the x components of both of E1 and E2. So let's draw this out. So we know that we have a angle theta right here, and this is distance r. Since we have let's see, what's the best way to go about this? Oh, right, okay. So basically here in our equation, we want to use our Coulomb's law. So we have Q, and then our distance is actually, we want to use sine theta because we have basically these components right here. And since you have theta there, if you do sine theta, you'll get this blue component. So we'll have our Q sine theta over 4 pi epsilon naught. And then I can also do times 1 over r squared. And we'll do the same actually for our other charge. Okay, and we see that since both of these add, our electric field here is E equals 2Q sine theta over 4 pi epsilon naught r squared. Yeah, so we have a 2 there because we're just adding both of these x components. But we don't want to just leave it as sine theta. We actually want to put that in terms of in r. So we have basically d divided by r is equal to sine, or d over 2 divided by r is equal to sine theta. So we just have d over 2r. Just use SOHCAHTOA. And if we want to get our r value here, we can actually represent it as square root of d over 2 squared plus z squared. If we just look here, we're getting r as, this is z, we have this is d over 2. Pythagorean theorem shouldn't be that much of a jump. So then we can go here, I'll write this out in red, our kind of final answer here, not with an eraser. So our electric field is equal to 2q times sine theta, which we actually just saw is d over 2r. So we'll have 2qd, our 2r will go in the denominator here. And we'll have our 4 pi epsilon naught, and we need to put in that 2r. So we have a 2, and then instead of actually putting r in, I'm going to say first that we have r squared times r, because remember, I'll just keep it as r now, just to not make too many jumps in the steps. So we have r squared times r, which is r cubed. So then we can say electric field is equal to 2qd over 4 pi epsilon naught times 2. So we say, r cubed is actually equal to that square root cubed. So an easier way of saying that is just d over 2 squared plus z squared, all to the 3/2 power, because we have r squared and r. So after that, we can just plug that in here. So we have d over 2 squared plus z squared to the 3/2 power. And remember earlier I said that the z direction components cancel out and we add in the x direction. So simply this will be our x hat, we can simplify this just a little bit. So, well, the only thing we can simplify actually is just these 2's here. So just to write it out one more time, and I'll write it out in blue, is the electric field is equal to QD all over 4 pi epsilon naught times d over 2 squared plus c squared to the 3/2 power in the x hat direction. And just as a quick review, this is the, okay, I'm just gonna circle this answer, but I also just want to show really quickly that our we have our electric field in its most generic sense. We have equals 1 over 4 pi epsilon naught times the sum, let's say I equals 1 to n, of qi over ri squared in the direction of r. So I just wanted to show that because right here, that's how we got that form over there. So we have our 1 over 4 pi epsilon naught, then we have our q, and then we have the r squared, and then our r hat vector is basically coming from this x direction being sine theta, because we have, sine theta is equal to our opposite over hypotenuse. So it's d divided by 2 over r. So that's why I was able to, because we're looking at this part here. We wanna use the that for our r hat. So that's why we can say that we have q times for our r hat, our sine theta over 4 pi epsilon naught, and then times 1 over r squared. See if that makes sense to you, because that's a really important thing for this problem, and that's really the main, I think, challenge for this one. And the rest of it is not that hard. So after that, you get this problem, and then you are good. Thanks for watching.